Good morning class. Today we discuss bond enthalpy. Student, bond enthalpy is defined as the amount of energy required to disassociate one mole of bond between the atoms in the gaseous molecule. I repeat it again. Bond enthalpy is defined as the amount of energy required to disassociate one mole of bond present between the atom in the gaseous molecule. Bond enthalpy is calculated with the help of formula. Bond enthalpy is equals to summation bond enthalpies of reactants minus summation bond enthalpies of product. Now let us discuss a numerical based on it. In the question we have to calculate change in enthalpy. Equation is given and the bonds and their respective bond enthalpies in kilojoule per mole are given. For solving this type of numericals, first we write down the structure of the reactant and product involved in the reaction like this manner. Here C2H4 on combustion give carbon dioxide and water. So the structure of C2H4 is written like this manner. Oxygen is like this manner. Carbon dioxide represent like this manner, and water is represented by this manner. Now we know that the bond enthalpy is equal to the sum of bond enthalpies of reactants minus summation bond enthalpies of product. Here the reactants are these and the product are these. Now here we notice 1, 2, 3 and 4. 4C single bond H bond, 1 carbon double bond carbon bond, 3 O single double bond O bond. These are the reactants. Now the products are 4 of CO, because 1 and 1 2 and 2 multiplied by 4 CO bonds, and 4 is OH bond. Now putting the values according to the table, we get bond enthalpy is equal to 4 multiplied by C single bond H. C single bond H value is 414 plus 1 single carbon double bond carbon, its value is 619. 3 bond of C O double bond O, that is 3 into 499. These are the reactant minus product are 4 molecules of CO. CO bond enthalpy is 724 and 4 of OH it is 460. Now we are just putting the value of carbon single bond hydrogen, carbon double bond carbon, O double bond O, C double bond O and O single bond H in the according to format. We get bond enthalpy is equals to, now on solving this we get approx 3772, and on solving this we get approximate equal to 4736. Now on calculate we get approx answer in kilojoule per mole. Now on solving we get answer in kilojoule per mole. It is approximate minus 964.0 kilojoule per mole. So we can solve this type of numerical which is based on bond enthalpy. It must be noted, for calculating bond enthalpy we must subtract bond enthalpies of reactant minus bond enthalpies of product. Now let us discuss the first limitation of first law of thermodynamics. Student, first law of thermodynamics could not explain the spontaneity of the reaction. I repeat again. The limitation of first law of thermodynamics is it could not explain the spontaneity of the reaction. Student, there are two types of process are there. First is a spontaneous process and the second is a non-spontaneous process. A process is said to be spontaneous if it takes place by of its own or by just initiation. For example, stone rolling from hill is a spontaneous process because it takes place by of own or by just initiation, while the process is said to be non-spontaneous if it not take place by of its own or by initiation. For example, pumping water from ground floor to top floor is an example of spontaneous process. Now, let us discuss entropy. Student, entropy is defined as the degree of disorder or randomness of a system. I repeat it again. Entropy is defined as the degree of disorder or randomness of a system. Entropy is indicated by letter capital S. It is a state function because it depends on the initial and the final state of system but not the path followed by it. I repeat it again. Entropy is defined as the degree of disorder or randomness of a system. It is a state function because it depends on initial and the final state of system but not the path followed by it. Delta S is equals to SF minus Si. If we are considering the case of solid, liquid and gases, in case of solid, particles are closely packed, so the randomness of particle is least. Therefore, it has less entropy as compared to liquid, as compared to gases. In solid, and degree of randomness is least, while in gases, degree of randomness is more. So, it is the correct order of increasing order of entropy in solid, liquid and gases. It should be noted, if the value of change in entropy is positive, then the process is said to be spontaneous. That is, process is said to be spontaneous if it takes place by of its own or by just initiation. If the value of delta S comes out to be 0, the process is said to be in equilibrium. If the value of delta S comes out to be negative, then the process is said to be non-spontaneous. So these are the conditions for a system to be spontaneous, non-spontaneous or in equilibrium. The unit of entropy is joule per Kelvin per mole. Now let us discuss entropy change during phase transformation. Entropy change during phase transformation. Number first is entropy of fusion. Entropy of fusion is indicated by letter delta S fuse. It is the entropy change when 1 mole of solid melt at the melting temperature. That is, delta SF is F delta S fuse is equals to S liquid minus S solid, or which may be equal to delta H fusion upon T M. Here the Tm is the melting temperature. Here Tm is the melting temperature and delta H fuse is the enthalpy of fusion. Now let us consider the second one. It is the entropy of vaporization. Entropy of vaporization is indicated by letter delta S vap. It is the entropy change when 1 mole of liquid changes into gaseous state at the boiling temperature. That is, delta S vap is equals to S vap minus S liquid, or we can write it delta H vap upon Tb. Here Tb is the boiling temperature. Number third is the entropy of sublimation. Entropy of sublimation is defined as the entropy change when 1 mole of solid changes into vapor state below the melting point of solid. That is, delta S sub is equals to S vap minus S solid, or it may be equal to delta H sub upon T. Here delta H sub is the enthalpy of sublimation and T is the temperature which is below the melting point. Here we discuss entropy change during phase transformation. Number one is entropy of fusion. It is entropy change for conversion of 1 mole of solid into vapor state. Second is entropy of vaporization. It is entropy change when 1 mole of liquid changes into vapor state at the boiling temperature. And the entropy of sublimation is entropy change when 1 mole of solid changes into gaseous state without converting into liquid state below the melting point of solid. So these are the entropy change during phase transformation. Now let us discuss the second law of thermodynamics. According to the second law of thermodynamics, entropy of universe always increasing. I repeat again, according to second law of thermodynamics, the entropy of the universe is continuously increasing. The second law of thermodynamics says that entropy of universe is continuously increasing. Now let us discuss the most important term of this chapter, that is the Gibbs free energy. Gibbs free energy is represented by letter capital G. It's a Gibbs free energy. Gibbs free energy is defined as the total available energy of a system which can be converted into useful work. I repeat again, Gibbs free energy is defined as the total available energy of a system which can be converted into useful work. It is represented by letter capital G. It is a state function because it depends on the initial and the final state of system but not the path followed by it. In mathematical, G is equals to H minus Ts. Mathematical Gibbs free energy is equals to enthalpy minus temperature into entropy. Suppose initial state G1, H1 and S1 is there. At final state G2, H2 and S2 is there. Now on subtracting, G2 minus G1 is equals to H2 minus H1, taking T common, S2 minus S1, we get delta G is equals to delta H minus T delta S. So it is the formula by which we can calculate Gibbs free energy. Here one thing must be noted, if the value of delta G is negative, I repeat again, if the value of delta G is negative, the process is said to be spontaneous process. But if the value of delta G is 0, that means the process is in equilibrium. If the value of delta G is positive, then the process is said to be non-spontaneous process. For a reaction to be feasible, delta G must have negative value. Delta G value must be calculated with the help of formula summation delta G naught of products minus summation delta G naught of reactants also. Summation delta G naught of reactants. It is the formula by which we can calculate delta G also. There is a relationship between Gibbs free energy and the EMF of cell. It is delta G naught is equals to minus NF E naught cell. N is the number of electron loss or gain. F is a Faraday constant. Its value is 96,400. The value of F we taken for simplicity is 96,500 coulomb. N is the number of electron lost or gain. There is a relationship between the Gibbs free energy and the equilibrium constant. It is delta G naught is equals to 2.303 RT log base 10 Kc. Here Kc is the equilibrium constant. Here Kc is the equilibrium constant. Now let us discuss the third law of thermodynamics. According to the third law of thermodynamics, entropy of perfectly crystalline solid taken to be 0 at absolute 0 temperature. I repeat it again. According to the third law of thermodynamics, entropy of perfectly crystalline solid taken to be 0 at absolute 0 temperature. Student, third law of thermodynamics are used in calculation of absolute entropies of substance at room temperature. I repeat again. Third law of thermodynamics is used in calculation of absolute entropies of substance at room temperature. Thank you very much.